Swayam Prabha. Digital India. Educated India.
Okay, so in this module, we will talk about the path equation for the satellites in a nearly circular orbits. So what is the modification in the path equation that occurs when we perturb the orbits by an infinitesimal disturbance? Okay, so again, let me just write what I just said. Nearly, we are going to talk about nearly circular orbits. Okay. So, let us say to begin with, suppose our particle under consideration P, suppose particle P moves in a circular orbit. Particle P moves in a circular orbit of radius A under the attractive force F of r per unit mass. Okay, and let us say that the speed, now since we are talking about a motion in a circular orbit, it is only possible when the speed satisfies the Newton's law. So it implies this is only possible when the speed satisfies the equation v square by a is equal to f of a, where a is my radius. So a is my radius. Okay. So then, so that is my normal equation of motion in the normal direction, and the equation of motion in the tangential direction is the conservation of angular momentum, which is L square is a square v square, right? So, and using this information here, we get that this is also equal to a cube f of a, and now suppose P is now slightly perturbed. P is slightly perturbed by a small impulse. And what we get is that the path of P now follows a new path, which is given by P moves on to a new path given by u is equal to 1 over a 1 plus zeta of theta, right? So zeta is the variable which is our perturbation. So this is my perturbation that I have added in the path equation, right? So now eventually, so I want to find now what is this zeta. So again, I plug this variable u, which is in this form, in my path equation. So when I plug this in my path equation, which I derived in the previous module, I see that my path equation for zeta is as follows. So this is dd square zeta plus 1 plus zeta is equal to 1 plus zeta minus 2 divided by f of a times f of a by 1 plus zeta, right? So what we have is that this is my path equation for the perturbation zeta. Let me call this as double star, and I want to simplify this further, because this f, the form of f, is slightly inconvenient. So I'm going to write it in a more convenient form using our binomial expansion, right? So not binomial expansion, but Taylor series. So my f of a plus a1 plus zeta is f of a minus a zeta 1 plus zeta, right? And now I'm going to use my Taylor series expansion of f around the radius a. So I see that this is f of a minus a zeta 1 plus zeta times f primes a. So what have we got? Right. So f prime a plus a higher order terms. So higher order terms could be zeta by 1 plus zeta square. So this is the higher order perturbative terms. And I could further assume that my perturbation zeta is such that this is tiny. This is small. So which means that 1 plus zeta is roughly equal to 1. Right. So I'm going to use this information here in this expansion. And my new expansion now is f of, so I put this as an approximation sign. So this is approximately equal to f of a minus a zeta f prime a plus order zeta square. Okay, so that is my, let me call this as my approximation a. And the second is, look, 1 plus zeta to the power minus 2. That is, I want to expand this in binomial expansion as well. This is 1 minus 2 zeta plus order zeta square, right? So what I have done is I have used the binomial expansion here in this function 1 plus zeta to the power minus 2. So this is binomial expansion. Okay, now I plug, let me call this as equation number b. So I'm going to use a and b and I plug it into my equation double star. And what have I got is the following. What I have got is that my double star is now in the linearized form, which is given by d2 zeta d theta 2 plus 3 1 plus a f prime by f of a times zeta. This is equal to 0, and this is my linearized equation. Okay, so now this linearized equation has a very standard form. This is the similar to that simple harmonic motion, provided, let me call this coefficient as capital A, provided this capital A is negative. So let us look at the two cases when A is positive or when A is non-negative. So what we expect is, well, this is the case we'll discuss later. First, the other case, A is negative. So this is case 1. When A is negative, we expect that zeta will have the form A e to the power lambda theta plus b e to the power minus lambda theta, and we see that lambda is going to be, since A is negative, we will see that lambda will be positive, and we expect the solution to blow up. Solution to blow up. And that is something, so what it means is that this perturbation, so this zeta is going to go to infinity, and that is a contradiction because we have assumed that zeta is a tiny number, right? So it's a perturbative number, perturbative value, and it cannot happen that it goes to infinity. So we are going to reject this case. And the second case is A is greater than equal to 0, and in that case zeta will give you a bounded form, and the bounded form is as follows. Let me call this A to be equal to omega square, where omega is a real number, so it's a real number, and zeta in this case is A cos omega theta plus B sin omega theta. Okay, so then so this is my bounded solution for the perturbative function. for the perturbation. Now, let us look at a specific case when my function a is of the is of a standard form. So specific case. So let us look at the case that we are going to deal more often. So the case is that f is of the form of a power law. So let us say my f of r is k r, f of r is k r to the power nu. So this is a power law. Okay. By the way, the central, most of the central fields and including the inverse square fields also fall under the category of power law. So power law is a more general form. So which means that f prime a over f of a is going to give us nu. So that is this quantity here. And once we plug, we see that our a from here, our a comes out to be nu plus 3. Right? So a is this quantity which is inside this square bracket. So a is nu plus 3. And we want that case, so let me call this as case 2 and case 1. So case 2 holds if my nu plus 3 is greater than 0 and nu, so which means nu is greater than minus 3, and this will close, which means that what have we got? So nu is greater than minus 3. We also want the orbit to be closed, right? So we also want the orbit to be closed, which means that this parameter has to be, this nu minus 3 has to be an integer. So we can write nu to be equal to m square minus 3, where my value m is an integer. Okay. It doesn't matter, an integer, positive or negative, we are using an m square. Okay, so why is that the case? Because we want the orbits to be bounded, not just bounded, we want the orbits to be closed as well. We had just seen that is only possible when the revolutions, the orbits are an rational number times 2 pi, or a number of revolutions, right? So that is why this relation is coming. Now let us look at some specific cases of nu. One specific, so what happens when m is equal to 1? So nu, which is m square minus 3, I get that nu is equal to minus 2. So m is equal to 1, which is nu equal to 2, is the inverse square law. Inverse law, right? So we see that my f of r is k by r to the power 2. Right? So that is my f of r. Now for m equal to 2, nu is 1. Right? So what is nu equal to 1? So now this is the case when we are talking about the simple harmonic motion, because f of r is k times r. So when we have a restoring force which is linear, we are talking about simple harmonic motion, and we know that that is, of course, that is bounded, right? Similarly, we can say that for m equal to 3, 4, 5, where nu are correspondingly, the value of nu will be 6, 13, 22, and so on, right? We expect that the solution will be bounded and the solution will be closed, right? So that is what we expect. We expect the solution to be closed. We expect the solution to be closed, and so that is, so what have we got? But there is a twist in this story here. The twist is, so far we have only looked at we have only looked at the fact that the small, when we are looking at the small parameter, we have expanded the functions only up to first term, the linear term. However, if we add higher order terms, for example, if we add, so adding order zeta square terms in my path equation here is double star. Okay, so adding order zeta square terms in double star, we see that my path equation is going to be such that nu equal to 6, 13, 22 and higher order values of nu are not closed. So this exercise can be repeated for higher order terms, and we are going to get to the conclusion that these values, they do not follow the trend that we expected in the linear case. So what is the moral of the story? The moral of the story is that only m equal to 2 and m equal to 1, which corresponds to the inverse law and the simple harmonic motion, are going to give us closed and bounded solution, right? So let me write down this statement. Only power laws for which all bounded orbits are closed, only power laws all bounded orbits are closed, are the simple harmonic motion and the inverse square laws. Okay, so the only power laws for which are bounded are the simple harmonic motion and the inverse power laws, and this result is not just a result which I have mentioned, but it is in the form of a theorem known as the Bertrand theorem. The Bertrand's theorem, a very powerful theorem which states that if you want a closed and a bounded orbit, you need not go further beyond an inverse square law or a simple harmonic motion, right? A very elegant result. Okay, so we need to see how elegant and how delicate this result is. If you want to see, let us look at the case of a real life example case of the precession of Mercury, the planet Mercury. And we want to let us add a small disturbance, a small wobble in the orbit of the Mercury, and let us see what happens. Okay, so what we are talking about is the precession of the perihelion. Perihelion means the point of closest approach. The perihelion of Mercury, of the perihelion of Mercury. Okay, so what we have is, since the inverse square law leads to closed orbit, while similar laws do not. I mean, I'm just stating the Bertrand's theorem. Laws do not, right? It provides us an extremely delicate test for the laws of gravitation. So this is an extremely delicate test. We are going to see with an example. An extremely delicate test for the laws of gravitation. Okay. So what have we got is, suppose we look at the central force field, which is in the form of an inverse square law. So f of r is gamma divided by r square. Gamma is our m naught g, which is a constant, m naught being the mass of sun. And with this inverse square law, let us add a small wobble in the form of epsilon, right? So our epsilon is a small parameter which is added to the power of the inverse square law, and of course r is the radial distance, so r is greater than 0. And now in this case, my a in the path equation, again we go back to the exercise that we did few minutes back, and we find out a comes out to be this time nu plus 3 to the power half. Well, this is not a, this is a nu plus 3, and we see that nu is minus 2 minus epsilon. So this is going to be 1 minus epsilon, right? So from here my I don't want to work with A, I want to work with omega, capital omega. So from here my omega is square root of 1 minus epsilon, right? So omega square is A. So this is, I can use binomial expansion. So this is roughly equal to 1 minus epsilon to the power half plus order epsilon square and so on, right? So 1 minus epsilon to the power half plus order epsilon square and so on. And what we have is that the perturbed orbit does not close. But in this case, well, because omega is not exactly an integer, the perturbed orbit this time will not close, but will have an apsidal angle, given by alpha, which is equal to 2 pi by omega, or 2 pi by omega. Omega is what we just found, and this is equal to 2 pi times 1 minus epsilon by 2 plus order epsilon square, and this is equal to 2 pi. What have we got? Well, this is 1 over omega, so the binomial expansion will include a plus here. So 2 pi plus pi epsilon plus order epsilon square, right? And which means that the successive, so what is happening is this alpha is the angle with which each sector of the revolution makes with the apsidal distances, right? So what means is that with every advances, the planet Mercury is going to go, it's not just going to, it is going to cross one revolution at every, every revolution it is going to cross 2 pi by a magnitude pi epsilon, right? So which means what I have just said, the successive perihelion will advance, annually by a small angle pi epsilon. Will advance annually by a small angle pi epsilon, and for Mercury this epsilon, the data is given, the data is there for Mercury. So for Mercury, the perihelion advances by this value. The perihelion advances by 43 seconds per century, right? So which means that every 100 years the angle, the epsilon angle has exceeded 2 pi by 43 seconds of the arc, right? So this is equal in terms of radians, this is equivalent to 5 into 10 to the power minus 7 radians per revolution, okay? And so this is my pi epsilon, that is this quantity, this is the advance that I was talking about. So this is my pi epsilon, and from here I can find that epsilon is this, let me call this as theta. So this is theta over pi, comes out to be approximately 1.6 into 10 to the power minus 7 radians per revolution. So it turns out that even Einstein's theory of relativity predicted that the precession of Mercury is going to happen, and it is going to precess by an order epsilon given by this value. So this simple Newtonian theory actually corroborates the Einsteinian theory of the precession of Mercury. So that is the power of this Kepler's laws of physics here. So then let us look at one more quick example of an inverse square field and look at the case of look at the path equation for that case. So we are talking about the attractive inverse square field. The attractive inverse square field. So suppose f of r is minus gamma divided by r square, where gamma is greater than 0, and f of 1 over u is minus gamma u square. This is my attractive law here, and we plug it into my path equation. And we see that this is d2u d theta 2 plus u is equal to, my path equation will give us that this is equal to plus gamma over L square, right? And from here, look, this is a simple linear equation. This is an attractive square field. Linear equation, we can quickly solve. U theta is equal to a times cos theta plus b times sin theta plus gamma over L square, which is the particular solution for u. And I can write this path equation. Remember, u is 1 over r. So I can write this path equation to be equal to 1 over r is gamma by L square times 1 plus e cos theta minus alpha. I mean, I can find e and alpha in terms of these constants a and b, right? So I call this, so this is my polar equation. This is my polar path equation, the polar equation of a conic. People who have studied basic conic sections will quickly familiarize themselves that this is the polar equation of a conic section with eccentricity E and center O. Right, so this is a polar equation of a conic section with eccentricity E and center O, and my alpha is the angle between the major axis and the initial line at theta equal to 0. Right? So this is the polar equation. So if people who are not familiar with the conic sections, we are going to we'll briefly do a quick crash course on conic sections in the next module. So you just wait for the next module. But in the meanwhile, I just want to conclude our current discussion by noting the following. That look, what we have found is that if we have an attractive square field that leads to a conic section, and people who are familiar with the conic section, for E less than 1, this is the familiar conic of an ellipse, right? So what we have is E less than 1 is an ellipse, E equal to 1 is the parabola, and E greater than 1 is the hyperbola. So people who are familiar that for E less than 1, we have found the equation of an ellipse. So that brings us to the Kepler's first law, which tells us that the motion, the planetary motion, the bounded planetary motion are in the form of an ellipse. Remember, both parabola and hyperbola are unbounded. So the only bounded motion for the planets are in the form of an ellipse, which is what the Kepler's first law tells us. So that completes our description of the 3 laws of Kepler in this module. So thank you so far for listening. Thanks a lot.